In the last step, we have proved that mu k equal to infimum of lambda f such that infimum is taken over all f with k less than f for any compact set k. Now, next step, step 3, if V is an open set, then mu V is equal to supremum of mu of k contained in V, k is compact. That is, for if V is an open set, then mu of V is equal to supremum of mu of k, where supremum is taken over all compact sets k contained in V. Then for the proof of step 3, we have set of mu k contained in V, k is compact, is bounded above by mu V. Then by the it is by the monotone property, that is k contained in V implies mu k is less than or equal to mu V. Now choose an alpha less than mu V. Then we will show that there is a compact set k such that k contained in V and alpha less than mu k. Here note that instead of taking mu V minus epsilon, we are taking alpha less than mu V. This is because this mu V may be infinity also. For any open set, mu of V may be infinity. So, alpha less than mu V, we will show that there is a compact set k such that k contained in V and alpha less than mu k. Since alpha less than mu V is equal to supremum of lambda f, supremum of lambda of f such that f less than V, there exists an f less than V such that alpha less than lambda f, because mu V is the least upper bound. So, alpha less than mu V means alpha is not an upper bound for the set. So, there exists an f less than V for which this lambda f is greater than alpha. So, here we have taken f to be less than V. So, take k equal to support of f, then we have k is a subset of V. Now, for any open set W containing k, then support of f contained in W, so we have f less than W, so lambda f less than or equal to W. So, this is true for all W containing k, and hence taking infimum over all such open sets. So, listen, for every f less than V, we have lambda f less than or equal to W. So, lambda f less than or equal to infimum of mu of W, infimum of mu of W such that k contained in W and W open. So, lambda f less than or equal to mu k. Thus, k is a compact subset of V with alpha. Lambda f less than or equal to mu k and alpha less than lambda f implies alpha less than mu k. Thus, we have constructed a compact set k such that k contained in V with alpha less than mu k. That means alpha is not an upper bound. So, we have mu V is an upper bound and no number less than alpha less than mu V is an upper bound. Thus, mu V is equal to supremum of mu of k, k contained in V, k is compact. This is true for all open sets. Now, next step, suppose E is equal to union I equal to 1 to infinity EI, where E1, E2, etc. are pairwise disjoint members of MF, then mu E is equal to sigma I equal to 1 to infinity mu of EI. In addition, if mu E less than infinity, then E belong to MF. Something like countable additivity. If E1, E2, etc. are members in MF which are pairwise disjoint and E is union of that, then mu E is equal to sigma I equal to 1 to infinity mu of EI. If in addition this mu E is finite, then E belong to, that union is also belong to MF. Then we first prove that if K1 and K2 are disjoint compact sets, then mu of K1 union K2 is equal to mu of K1 plus mu of K2. For that, let K1 and K2 be disjoint compact sets. Let epsilon greater than 0 take V is equal to x minus K2. Then we have K1 contained in V because K1 and K2 are disjoint. By Urysohn lemma, there exists an F belong to CCX such that K1 less than F less than V. Then we have Fx equal to 1 on K1 and Fx equal to 0 outside V. So Fx equal to 0 on K2 and 0 less than or equal to F less than or equal to 1. Then by step 2, mu of K1 union K2. Note that if K1 and K2 are compact, K1 union K2 is compact. So mu of K1 union K2 equal to infimum of lambda F such that K1 union K2 less than F. Hence, there exists a G belong to CCX such that K1 union K2 less than G and lambda G less than mu of K1 union K2 plus epsilon. Here also we use the properties of infimum. Mu of K1 union K2 is equal to infimum of lambda F such that K1 union K2 less than F. This is proved in step 2. So, there exists G belong to CCX. So, for any epsilon here also we start with an epsilon. We started with epsilon greater than 0. For this epsilon greater than 0, we get that this mu K1 plus epsilon is not a lower bound for this collection lambda F such that K1 union K2 less than F. So, there exists a G such that K1 union K2 less than G and lambda G less than mu of K1 union K2 plus epsilon. Then we have Gx equal to 1 on K1 union K2, Fx equal to 1 for every x belong to K1, 1 minus Fx. Listen, Fx equal to 0 on K2. So, 1 minus Fx equal to 1 for every x belong to K2. Hence, Fg equal to 1 on K1, 1 minus Fg is equal to 1 on K2 and 0 less than or equal to Fg less than or equal to 1, 0 less than or equal to 1 minus Fg less than or equal to 1. So, K1 less than Fg and K2 less than 1 minus F into G. Since lambda is linear, mu of K1 plus K2. So, since K1 less than Fg, mu of K1 less than lambda Fg, K2 less than 1 minus Fg, mu of K2 less than lambda of 1 minus F into G, which is G minus Fg, and therefore mu K1 plus mu K2 less than or equal to lambda Fg plus lambda G minus Fg, which is equal to lambda G, and this lambda G is less than mu K1 union K2 plus epsilon. So, this is less than mu of K1 union plus K2 plus epsilon. Since epsilon greater than 0 is arbitrary, we have mu of K1 plus mu of K2 less than or equal to mu of K1 union K2. Hence, mu of K1, and it is clear that mu of K1 union K2 less than or equal to mu of K1 plus mu of K2 that we have proved earlier. So, mu of K1 union K2 is equal to mu of K1 plus mu of K2. Now, if mu is equal to infinity, then by step 1 mu is equal to sigma I equal to 1 to infinity mu of Ei. If mu is equal to infinity, then sigma mu e less than or equal to sigma I equal to 1 to infinity mu of Ei. If this is infinity, we have this also infinity by step 1. So, let mu e less than infinity. Then, start with an epsilon greater than 0. Since Ei belong to MF, Ei belong to MF means mu of Ei less than infinity and M of Ei is equal to supremum of mu of k such that k contained in EI, k is compact. So, by that we can choose a compact set. For each I, we can choose a compact set Hi contained in EI such that mu of EI greater than mu of EI minus epsilon by 2 raised to I. Since H1, H2, etc. Hn are compact, for every n, Kn is equal to H1 union etc. Hn is compact. This is because finite union of compact sets is compact. Thus, Kn is a compact set for each n and Kn definitely contained in E. Therefore, for n equal to 1 to etc., mu E greater than or equal to mu of Kn, which is equal to sigma I equal to 1 to n mu of Hi greater than sigma I equal to 1 to n mu of Ei minus epsilon. Since this is true for every n and for every epsilon greater than 0, we have mu E greater than or equal to sigma I equal to 1 to infinity mu of Ei. Here letting n tends to infinity, we get, actually first letting n tends to infinity, we get mu of E greater than or equal to sigma I equal to 1 to n mu of Ei minus epsilon. Since epsilon greater than 0 is arbitrary, we get mu of E greater than or equal to sigma I equal to 1 to infinity mu of Ei. Now, if mu E less than infinity, we have that series sigma I equal to 1 to infinity mu Ei, which is equal to mu E, that is less than infinity. This series is convergent. If series is convergent, the n tail of the series converges. N tail tend to 0. N tail means sigma n plus 1 to infinity mu Ei tend to 0. So, there exists, for corresponding to any epsilon greater than 0, there exists n belong to n such that sigma n plus 1 to infinity mu of Ei less than infinity. Hence, mu E less than or equal to sigma I equal to 1 to n mu of Ei plus sigma n plus 1 to infinity mu of Ei, which is less than epsilon. So, we get mu of Ei, mu of E less than or equal to sigma I equal to 1 to n mu of Ei plus epsilon. Now, sigma I equal to 1 to n mu of Ei, for every I, mu of Ei is less than mu of Ei is less than mu of Hi plus epsilon by 2 raised to I. Here actually mu of Hi greater than mu of Ei minus epsilon by 2 raised to I for each I. This means mu of Ei is less than mu of Hi plus epsilon by 2 raised to n. So, this is true for I equal to 1 to etc. up to n. So, we have this less than sigma I equal to 1 to n mu of Hi, actually mu of Hi plus epsilon by 2 raised to n. So, when you take the summation, this one mu of H1 plus mu of H2 plus etc. mu of Hn is nothing but mu of Kn. Mu of Kn equal to sigma I equal to 1 to n mu of Hi for each n equal to 1 to etc. In particular, this n equal to capital N, that is true, and plus epsilon by 2 raised to I plus summation epsilon by 2 raised to n, which will be equal to epsilon itself. So, less than mu of Kn plus 2 epsilon. Hence, Kn is a compact set such that Kn contained in E and mu of E less than mu of Kn plus 2 epsilon. To get, if you want to get this mu of Kn, mu of E less than mu of Kn plus epsilon, in the rest of the proof you may use epsilon by 2, so that this is less than mu of Kn plus 2 epsilon. Hence, mu V is equal to, so we have shown that mu E is equal to, supremum of mu of K such that K contained in E, K is compact. For that, mu E is an upper bound. Mu E is equal to mu e is an upper bound for the set, and mu e minus 2 epsilon is not an upper bound. So mu e is equal to supremum mu k contained in E, k is compact, therefore E belong to MF.